How are you? How are you doing? Yes, I mean you watching. First of all, you must be a further math student, right? Master, further math is not easy. It's not easy at all. So there's one question like that is a little bit you. I'm going to present the question to you watching. You think that is very hard, but by the end of the video, you realize that you will love the equation. You will want the equation to come, but it's not going to come. Anyways, all right. Hello guys, welcome once more to another video on YouTube channel. Today we are going to be looking at equation on complex numbers, guys. It's not easy. Okay, let me stop playing now. This question has been sent to the Mafa group, and with my phone here I just received the equation, so I decided to solve the equation. And because some people are complaining that they are not understanding somebody's solution, so I decided to make a video. So we have a complex number z is equal to half times cos theta plus I sin theta. That's a complex number. The first question is asking us to prove that z to the n is equal to something. So we have to show that z to the n is equal to 1 over 2 to the n times the cosine of n theta plus I, the sine of n theta. Voila, I like this type of things. Okay, so let us prove straight away, very fast. Follow me. E to the I theta, basic definition, it is cos theta plus I sin theta. Do we agree? Yes, you agree. I know very well that you agree. Now half times e to the I theta is half times cos theta plus I sin theta. You agree. I know that you agree. But this man on the right hand side is my z. So what can we conclude? First of all, that z is equal to half times e to the I theta. Now raise both sides to the power n. What are you going to have? Z to the power n is equal to half e to the I theta raised to the power n. What is indices saying? I'm going to say z to the n. I'm going to raise the half to the n. Then I raise the e to the I theta to the n, right? So this is the same as 1 over 2 to the n. And this I can write it as e to the I. Now, very special, I'm going to put n theta in bracket. This n theta now here becomes my argument. Okay, it becomes my new argument. So at the end of the day, I just have my z to the n to be equal to 1 over 2 to the n. Now I transform this guy back into the trigonometric form. So I'm going to have the cosine of the argument plus I, the sine of the argument. I think you can complete it. The proof is complete. So don't be looking as if don't be looking this thing as if it is witchcraft, please. Further math is easy, guys. Further math is easy. It's very easy. I'm lying, it's complicated. It's not easy to know this thing. So guys, make sure you watch the videos all the time. Okay, now the second proof we need to show is using the Moivre's theorem according to the equation in front of me. I'm going to the next slide there. So if you want to capture this thing, please capture it fast. Okay, I suppose I have captured. Okay, so if I read the equation, it's saying again, using the Moivre's theorem or otherwise, show that. Okay, now we need to show again. We need to show that. With a red pen. We need to show that. This is the next thing. The sum from where? From r equal to 0 right up to where? To infinity of what? 1 divided by 4 to the power r times what? The sine of 2r theta is a convergent geometric progression. This question is wrong. A sum cannot be a sequence. In fact, this sum can never simplify to a sequence. That's the first thing. Okay, so we are actually supposed to show that this a convergent geometric series, not sequence or not progression. So show that it's a convergent geometric, so that it's a convergent geometric series. Yes. Okay, follow me again. Very soon you are saying that it is hard when something is not hard at all. Follow me keenly, and at the end, if you tell me that it is hard, it means that now you have a problem, right? You have a problem. Guys, I'm writing, this pen does not want to come out there. Now I cannot use. Okay, let me divide again. Voila. So first of all, I would like you guys to look at this. First of all, to show that this is a convergent geometric series, I need to show that the sequence involved is a convergent geometric sequence. That's all. So if I'm able to show that the sequence involved is a convergent geometric sequence, then I have proven that this is a convergent geometric series. This is a sum to infinity. Okay. So the sequence involved, what is it? It is 1/4 to the arrow times the sine of 2r theta. That's the sequence involved. So first of all, I will want you to identify. Look at, previously we saw that z to the n is equal to 1/2 to the n times e raised to the power I n theta. What is this? I n theta. Voila, that's what we had. Now and we, in fact, we also saw that it is 1/2 to the power n into the cosine of n theta plus I the sine of n theta. Okay, now think about, if, see, you have a 4 here now, and this 4 is what? Is 2 raised to the power 2. So if I just think about, maybe, okay, let me let, like, I just love to let me let n to be equal to 2 arrow. Then look at what is going to happen. We are going to have z raised to the power 2 arrow to be equal to 1/2 raised to the power 2 arrow times the cosine. Are you understanding now? Are you seeing where I am going to? Plus I the sine of 2r theta. Hope it's making sense now. Now let me distribute. Remember that I can also do this man to have 4 before I raise it to the power arrow. Now let us distribute that guy. So we are going to have that z raised to the power 2 arrow is equal to, I will distribute this man 1/4 raised to the power arrow. I will distribute it to the first term, and the first term here is cos 2r theta, then plus I times what? The very man 1/4 raised to the power arrow sine 2r theta. Voila. Hope you're seeing something. Now you realize that this guy here, okay, is the imaginary part of this man. The imaginary part is the part that is attached to the complex number I. So I can say that 1/4 raised to the power arrow the sine of 2r theta is equal to the imaginary part of my complex number z raised to the power 2r. You see now, it therefore means that, what does it mean? Therefore means that if I take sum on both sides, okay, I'm going to have the sum from r equal to 0 to infinity of this man here. Means I cannot write it again now. Let me just put a box so that I should know that it is it. This is a box of this man is equal to what? Is equal to the imaginary part of what? The sum from r equal to 0 to infinity. Now this guy here, okay, we already saw earlier that it is actually now, if you simplify this thing, you are going to have 1. You are going to have, no, you are not going to have 1. You are going to have e raised to the power, this space is small. Let me just go to the next slide. See, z to the 2 arrow is equal to e to the power I theta over 2 raised to the power 2 arrow. That is it. Since z was just e to the I theta on 2 now. Okay, now you realize that this our sum now from r equal to 0 to infinity of 1 over 4 to the r, the sine of 2r theta is equal to what? The imaginary part, we saw it already, the imaginary part of what? Of the sum from r equal to 0 to infinity of z to the 2r, which is what? E to the I theta over 2, all that raised to the power 2r. Voila. So it therefore means that if the right hand side converge, then the left hand side will converge. That one is clear. Okay, if the right hand side converges, then the left hand side will converge. Now look at the sequence. If I let u of r to be equal to e to the I theta on 2, all that to the power 2r. In fact, we can simplify this and write this as e to the 2I theta over 4, because we need to square the 2 now. Then I'm just removing the 2 from the r, and I'm raising e to the I theta on 2 to that power 2, so that we get this right. In fact, guys, not to talk too much, what is inside here, what is inside here is a common ratio of that geometric sequence. Okay, and we know that first of all it is geometric because see, if I do ur plus 1 over ur, please, you are the one to do it, I'm tired. I'm going to have e to the 2, you guys have not worked anything, I'm the only person working, so e to the 2I theta divided by 4. If you do it very well, you are going to have this man. But now we know that if with this fact we can already say that you are geometric, you are a geometric series. Okay, now for you to converge, what should happen? The absolute value of ur plus 1 over ur has to be strictly less than 1. It is clear. The absolute value of this my common ratio here is equal to 1 over 4, because the absolute value is kind of the modulus. The absolute value of a complex number is its modulus. Okay, and the modulus of this man is 1 over 4, and it is less than 1, so it converges. Proof complete. Okay, now the most challenging part. Why am I even saying most challenging? I already simplified everything for you guys. Let's just go to that part now. That's the last. It's still a proof, man. This question was all about proving it. Okay, now that one is now saying that now using the previous informations, now show that the sum from r equal to 0 to infinity of 1 over 4 to the r times the sine of 2r theta is equal to, I'm seeing here 4 sine theta divided by 17 minus, this is 16 cos 2 theta. This is what I see. So guys, let us see if this is true. Let us see if this is true. Okay, so I think I'm going to use a different coloration. Yep, yes, I'm going to use a different coloration. No, Jesus, to keep people's children nice. Okay, let's use black. All right, so we have already seen previously that if I call this sum, right? Hey, what am I doing like this? Let me use a pen. If I call this sum s to infinity, I'm going to have what? S to infinity. That sum to infinity is equal to, we already saw that is what? The imaginary part of what? The sum from r equal to 0 to infinity of e to the 2I theta all divided by 4 raised to the power r. But we know that it converges, so it should just the formula should stay constant, a over 1 minus r. The common ratio here, we had it. Your a is gotten by replacing r with 0. If I replace this r with 0, the first term is going to give me 1. So I have a, we forgot about the imaginary part. We need to find that imaginary part. So we need to write imaginary part of, the first term is 1 divided by 1 minus, the common ratio was e to the 2I theta divided by 4. That was a common ratio. So guys, let us simplify. So it's equal to the imaginary part. If I multiply top and bottom by 4, I get 4. I have the 4 in the numerator. I have here 4 minus e to the 2I theta. Now I have the imaginary part of, now I have 4 divided by 4 minus, now e to the 2I theta is what? The cosine of 2 theta plus I, the sine of 2 theta. No argument, please, no argument. So this is the imaginary part of, now we have to rationalize. Okay, so to rationalize is very simple. 4 minus cos theta becomes a real part. It's clear. That's a part without I, so this is a real part. And then now sine 2 theta is now the imaginary part. So we are going to multiply the numerator by what? By the conjugate of the denominator, which is what? 4 minus cos 2 theta. Then the conjugate, I need to change the sign in front of the sine 2 theta, so the sign will become minus what? Sine 2 theta. That's a conjugate of the whole of this denominator. We just need to change the positive sign to the negative sign. Okay, now the denominator, we also need to multiply the denominator with its conjugate, but we know that if we multiply a complex number with its conjugate, to get the answer we just need to square the real part, okay, and then we add it to the square of the imaginary part. That is it. So guys, let us simplify. The imaginary part of what? The denominator, believe me, if you expand now, you are going to have 17 minus 16 cos 2 theta. Okay, now the numerator, let us expand. 4 times 4 is 16, then minus what? Minus 4 cos 2 theta, then minus, see a minus sign here, minus 4 sine 2 theta. Anyways, that's what we have. So at the end of the day, the proof is wrong. There was supposed to be a minus, let me go there, there was supposed to be a minus sign here, and this angle here was supposed to be 2 theta. Yes, I just believe that we have not made a mistake here. This angle here was supposed to be 2 theta. Okay, because the imaginary part of this complex number, there's an I that we missed. We just need to take the denominator alongside this other part, which will come back to the proof. Okay guys, like, share and comment. Thank you for watching, and see you guys in the next video. Yes, see you guys in the next video. I'll be very happy if I see you, though you cannot see me.